with our work. So it is a joint work with DJ Ambati and Professor Jaap van der Wecht and Professor Onno Bokhoven, who is actually here, but unfortunately he's not feeling well, so apologies for the weather. The outline of the talk is as follows. I will try to motivate you about what am I doing. What I'm intended to show today is a numerical method and prove that the numerical method is actually working. So in order to demonstrate the numerical method, I will start with a simple one-dimensional system, then show results, recover some known schemes, numerical schemes, recover some unknown schemes, at least unknown for me until the point. Then I will show how it works for water wave system in autonomous case. And then at very last, I will show a force system, waves generated by a wave maker. Here is the motivation. You see a wave tank from the Maritime Research Institute of Netherlands. It is a wave tank. Here on the left, you see wave makers installed. They are moving back and forth, generating various waveforms into the channel. It's interesting to have such a thing because you can study various waveforms, you can study wave impact on prototype oil platforms or prototype ships placed somewhere over here. Nevertheless, to test it, you need to know exactly what kind of sea state you are interested in. So generally it's possible to do inverse problem and then define how you should move the wave maker. Nevertheless, the opposite is also useful. It's useful to have a computational method which will create so-called numerical wave tank. So a wave tank with a moving boundary. As far as Marin was interested in such model, just in order to save space and time and money, because it's very expensive to run such an experiments all over again every time. It's better to set it properly starting from the beginning. They have assembled a number of experiments, measured it very accurately, and gave it away to various research groups, asking whether it is actually possible to simulate numerically the laboratory experiments they have performed. We took the challenge. Why is it actually a challenge? A computational domain is moving, accommodating both the movement of the free surface and the wavemaker motion. Moreover, the position of the free surface is a part of the solution itself. Also, as far as we are going to work with long time simulations and also waves will be propagating over long space, numerical energy drift is something you want to avoid. Otherwise, the wave will die too early and then we will not be capable of reproducing the experiment at the required place. To cope with the challenge, we decided to work, as many others, in variational approach. Nonlinear free surface gravity water waves been studied by many people. I will be referring to it as Miles variational principle, but of course here I have to refer to Luke and Zakharov and Bateman and Brewer and many others. It is a beautiful mathematical construction as all the dynamics are expressed just in a single functional. And then its form is directly associated with conservation laws as proven by Noether. Apparently, time integration was particularly non-trivial. And in order to be capable to find the proper time integrator, we constructed a very, very simple system first. So here you see just one-dimensional, 1 degree of freedom Hamiltonian system, where P and Q are the generalized momentum and coordinate, respectively, and H, so-called Hamiltonian, is the total energy of the system. Whereas system in nature can be expressed in such a form. So in one-dimensional, it will be like oscillating pendulum or a spring. So if there is no external forcing or damping, then the system will just run forever. Yeah, but I hope for damping. So when we apply the variational principle, find the extremes of the system, we obtain a Hamiltonian system of equations. Beautiful symmetric form, and it's a lot of research being done explaining how should one approximate the system appropriately. because the system is energy conserving and it has symplectic flow. So it's natural that one would like to have it also at the discrete level. Symplectic time integrators are designed specifically to keep the symplectic nature of the system. And our long time goal is to create a symplectic time integrator for nonlinear free surface gravity water waves, which are also can be presented in a Hamiltonian way.
Question?
Yes.
Could you go back one slide? So I can take the bottom part, say you're doing Hamiltonian mechanics, and I don't need to know anything about the line above. What's the relation between those?
It is so here the Lagrangian is an action functional. It is the difference between kinetic energy and potential energy, and you need to minimize it. And when you minimize it, then the solutions of the minimization problem will describe the system. Because what our system is trying to do is to find the place where it takes minimal energy. So it is trying to find the shortest waves between the transitions. Minimal action, yes.
It is not minimum energy, it is minimum action.
Action, yes.
Not necessary to minimize, it is a critical point. Hamiltonian principle is not minimization.
Yeah, to find the shortest way between the transitions.
Action.
Yeah. So when we take the action functional and take the functional derivatives with respect to the variables, we obtain a system of equations. This is a long time goal, and we can take already known symplectic time integrators, but we can also use a theory. As Martin and West has proven in 2001, if we take a variational approach to obtain the time discretization schemes, then they, by construction, will be symplectic under certain conditions. So what we are trying to do is to construct a discrete variational principle in time. We choose to work with discontinuous Galerkin finite element approach. Here you see time. We chop the time x into slices, into elements, and in each element we approximate our variables as polynomial expansions. So we can choose piecewise constant expansion, piecewise linear expansion, quadratic, and so forth. We allow our functions to be discontinuous over the time edges. Then we need to introduce the left and the right trace of a variable over the time edge or a time point. So first I will be using notation for any variable. N is a time point where it's placed, minus is the left trace, and plus is the right trace. And for further convenience, we will introduce a jump and average operator, which are formulated as follows. A jump, it is the difference between left and right trace, and an average is a weighted average, where the weights alpha and beta are summed to 1.
Question?
Yeah.
On the previous slide, if you go piecewise linear, what is there to be gained by not having continuity?
Yeah, apparently it's not a trouble. Apparently it's not a trouble. So apparently it's possible to have discontinuous variables in time.
No, but what he's asking, what is the advantage of having this continuous as of continuous?
Yeah, thank you. The point is that we will going to work in a space-time approach where time is just an extra dimension of simulation. And then we also need, as far as we are working with finite element method, we also need to know how to choose the the basis functions in time. And then when one works with classical representation, Pn plus 1, it's not quite clear what are the basis functions. So it was just a reformulation of a classical theory in this approach just to pick up the basis functions for the approximation base time. So I will try to show how we recover the known schemes in that approach. Then there is no change. Yeah, thank you.
Discontinuous in space as well, or?
In space it's possible to be discontinuous, but the results which I will be showing are just continuous. but yeah, it's possible. So what we do in order to construct a discrete variational principle is take the variational principle which you might recognize. We chopped the time domain into pieces. We substituted the polynomial expansions p and tau into the non-conservative product. We substitute our approximations in the Hamiltonian. And as far as we are working with discontinuous basis functions, we need to do something across the time edges. And it is so-called flux, which is established to exchange the information between the finite elements. And there is some freedom of choice given here. What can we vary is the polynomial expansions, p tau and q tau. Also, we can choose the quadrature rule to calculate the integral, because in general it's not possible to calculate it exactly. And also the weights in the flux term, alpha and beta, can be whatever we choose them to be. So first choice, the simplest choice, is to take 1 point quadrature rule, just piecewise constant basis functions. Then we substitute everything. And then apparently for two choices of alpha, we can construct either symplectic Euler scheme or the adjoint symplectic Euler scheme. So what we have, even though we formulate everything in terms of Pn plus and Pn minus, the structure is still the same. So we solve this guy, provided we know this guy, and we solve this guy, provided we know the previous guy. So it is a reformulation of the known result, but just at the moment there are just pluses and minuses in there. Even though there are 4 variables, I still reformulate the whole system into variable system. While taking the piecewise linear approximations and while taking the mixed trapezoidal midpoint quadrature rule for the Hamiltonian, we can recover 2 Sturm-Verlet schemes. It's also just a classical approach, and what we appreciated here is the basis functions. We just knew exactly what kind of basis functions we will need to take further in our calculations. Basically, it's just everything what we needed, but for curiosity, it's natural to ask, is it possible to derive anything new from this approach? Apparently, if one would take the trapezoidal rule in both variables and Lagrangian polynomials, substituting them into the variational principle will result in a fully explicit second-order scheme. It is fully explicit. The stability, linear stability criteria is just the one which was given for Sturm-Verlet and for Euler. Nevertheless, and it actually works for some systems. We tried it for linear potential flow and for shallow water waves. Actually, it works with second order. Everything is fine. But the system is somewhat tricky when you take it with some caution. Just take a harmonic oscillator, write down precisely the derivatives of the Hamiltonian, and then you may observe that the second equation and the third equation are kind of stick to each other and don't really interact with the first and the fourth one. So these 2 equations form some system. For first and fourth are forming a system. So Pn plus, Qn minus, and then they don't really interact. So it is a funny mathematical system, and it would be potentially interesting, of course, or it's nice to have fully explicit scheme, which is still symplectic. But yeah, I should say that one should treat it with caution. But we are trying to do something with it. So not really impressive, but actually we managed to make another novel scheme. We took a 3-point Simpson quadrature rule and then the quadratic approximations. We didn't quite know how to choose the weight, alpha. Then we considered the linear stability analysis. And then you see that the only region where we can consider very small delta t is alpha to be equal 1/2. Then taking the cross-section of this area, plotting it over here, we see that our stability range is over here. So it is somehow modulus of omega times delta t. is about 1.7 something, so it is a bit more restrictive than for Sturm-Verlet scheme. Formulating it explicitly, you see here the implicit system, 1/2 variables. You have to update them simultaneously, and then the leftovers are just 4 explicit equations. The system is symplectic due to its construction, but we also verified it analytically. As far as our variables are completely disjoint, this p minus and p plus, we can formulate it in 2-variable system, 4-variable system with 4 initial conditions. The transformation map is extended, but the simplicity condition is satisfied.
So is it symplectic because you're using Luke's variational principle, or is it symplectic because of your choice of flux?
Marson and West said that if you do continuous Galerkin, discontinuous Galerkin, then you will obtain symplectic scheme by construction, and he proves it as a theorem.
So what do you get with your choice of flux? Is that stability? Is it to be stable?
Yeah, we
Big
took
alpha?
this particular choice of flux because in perspective, when we will be working with discontinuous in space, we will be using this flux in space because it's been proven by previous student of Jaap, van der Wecht, and Tono that it has very good properties. So we just tried to do just the same thing here, and for curiosity, just have a look how does it work. So it could be chosen differently, and it's actually an interesting problem how to vary fluxes in order to get the properties which you actually would like to have. We verified this simple PQ system against an analytical solution. We got the third order of convergence. Nevertheless, it's quite a simple test, and the question is whether we can make something more complicated in there. The more complicated test case is Miles variational principle. As been discussed already many times, you see Miles variational principle with the kinetic energy and the potential energy. I call it the free surface elevation. Velocity potential is called phi, and velocity potential as a free surface is phi s. Our domain omega is varying time, provided the movement of the free surface. One can take the variations and then obtain the system of equations to solve. So how are we going to solve it? One could try to approximate these equations, but instead we decided to construct again a discrete variational principle. We approximate all our variables in space and time, plug it into the variational principle, take variations, and obtain a system of equations which, as I'm going to show, would have good properties, including an energy of absence of energy drift over long time simulations. So first we approximate our variables in space, substitute all of them. So it's a usual finite element formulation where M is mass matrix, A is a stiffness matrix. Our M matrix, mass matrix, is constant, while A matrix depends on the movement of the free surface, therefore it is time dependent. So here we don't have a space dependence anymore because we calculated these matrices over the whole domain. So everything, all the dependencies which we have at the moment here for this integral is just time dependence. Then we can use all the theory which we have constructed, then take the basis functions, plug them in, and have a look what we get. So for our free surface and velocity potential, we already know the approximation. So I just write down the explicit form of the quadratic expansions. So it is quadratic basis functions via 3 points. We see that if time is equal to Tn, then the only term which survives is this one, and so forth. With this explicit approximation, we can actually calculate the first integral. The other two, the total energy, we will approximate with the quadrature rule. It is over here, the Simpson rule with 3 points. And the term in red is the flux, which I already described, and for which we take already the chosen weight, 1/2. It's pretty ugly, so I'm not going to show more. So you just take the variations with the expansion coefficients and obtain system of equations to solve. So what I will be considering is standing waves with the solid walls, with a flat bottom. They're going back and forth. I run this test for 100 time periods, and then over 100 time periods, it's the energy plot. It is time, it is total energy. So from far away, you don't see any energy drift, decay, or rise. Zooming near the line, you see oscillations which are going back and forth, as it is predicted, but on average they remain the same. The deviation of the energy is not going anywhere, it's just constant. Also, the deviation of the energy is characteristic of the system itself. So when we take smaller and smaller time steps, we get smaller and smaller deviations. We perform this test, just take smaller and smaller time step, measure the deviation, and then we can also verify that there is a third order convergence for this scheme. So apparently there is a symmetric scheme which works for potential flow. Fine. It's just interesting here that there is an approach to derive known schemes and also new schemes. I don't know whether someone will find those new schemes useful, but I think it's just interesting that it's possible to do so in this approach. The next problem I'm going to consider is waves generated by WaveMaker. So with respect to the previous problem, the only thing we add is an extra forcing here. It is a moving wall which is going back and forth, generating various wave states in here. Our Miles variational principle will be reformulated slightly. This term will be added. You can see we allow only horizontal movement of the piston. It is described by the function r dependent on time. And if r doesn't depend on time, then this term switches off, and you have again just Miles variational principle in the Hamiltonian formulation. We take the variations, then the system of equations. The only equation which is different here is this equation saying that the wall is given velocity to the water at the wall. The approach we are going to take to simulate it numerically is just the same. We approximate the variables first in space, then in time. So first we approximated it in space. The formulation is a bit more difficult with respect to the previous test case, because now our mass matrices are time dependent because the domain horizontally stretches and springs. And also the basis functions will become time dependent on the free surface, which will give rise to this function. And then also the WaveMaker term will appear here. And actually it was quite difficult to approximate. It's why we started all this time discontinuous approach, because it was not clear at all where to take the forcing. So we need to approximate this term, which is time dependent, and where should we take it? In the middle, one side, another side, not clear. So what we took then is the Stormer-Verlet basis function approximations, analogous to the one which I was showing for a simple one-dimensional test case. So the basis functions are linear. Our variables are allowed to be discontinuous over time. There are discontinuities. We substituted, get a system of equations, its approximation of the Hamiltonian, 2 points, quadrature rule. Then we take variations and obtain the system of equations. To show how it works, I think the best is to show the comparison with the laboratory experiments. So we will be actually comparing it with a real laboratory experiment from the Maritime Research Institute of Netherlands. Here, the test case is a wave basin with a sloping bottom. The WaveMaker is placed here, moving back and forth. At the moment, our model is not capable to deal with run-up. And in the experiment, there is a run-up. Therefore, to deal with it, we place a solid wall over here. It's artificial wall. Therefore, we have to keep it in mind that when our wave will propagate, then it will reflect and then disturb the measurements, so we have to stop at the appropriate time. In order to compare the laboratory experiments with the numerical experiments, it is a number of wave probes being placed all over channel. They're placed here and here and here. They're measuring the wave elevation over time, the function of time. wave starts somewhere here, you see wave propagating, zooming in, you see quite irregular waves. Going, difficult to compare. Comparing the wave probe data, you see here red one is a laboratory experiment, and blue one is our numerical experiment. In one of the wave probes, which is somewhere in the first quarter, you see quite a good comparison over time. So it is the time x and it is wave height. It is the middle of the domain, and we see that the comparison goes pretty well. Performing a spectral analysis, so taking the laboratory data, performing a spectral analysis for it, taking the computed data in one of the chosen probes, performing spectral analysis. We collide them together, and we see that we reproduce the spectra quite well. It's somewhere in the first part of the domain, and it is somewhere in the middle of the domain. It was an irregular wave test case, and actually Marine has assembled more complicated test case with a focusing wave. You see that wave probes here are located all together because something will be going on in here, and we don't hear at all what's going on in here. So you see here the short waves are assembling, the long waves are coming. Zooming near the free surface, you see that a huge splash occurs. This splash is somehow 5 times larger than it was the incoming wave height near the wave maker itself. Then it doesn't break, it just smoothes out, goes back. Comparing the measured wave height and the numerical wave height, again in red and in blue, it is time, it is wave height, it is very beginning of the domain. We see that in the beginning we do fine. It is just where the waves are already accommodating to become a splash. We tend to underestimate the wave height. Nevertheless, we catch the time and the place of the splash quite nicely. And it is the splash itself, so it is about 5 centimeters over there. And then everything resolves, and our code has survived, which was actually quite a challenge to make the scheme stable enough to survive such kind of interactions. And then performing a spectral analysis, in the beginning of the domain, we see quite a good comparison. Near the splashing point, yeah, we tend to underestimate a little bit. Nevertheless, the comparison is quite good because we catch the range of frequencies. And here are the conclusions, a bit earlier than the time, but I hope you will excuse me, provided it's Friday. Yeah, we constructed a variational method to simulate water waves, and on the way we also constructed a variational method to construct time integrator schemes. It seems that there are some new schemes, so, and also it was an extra analysis for the new schemes because it was not quite clear what do those schemes actually mean. Thank you for the financial support and for providing us the data from the experiments, and thank you for your attention.
Questions?
For the wave maker problem, did you start the fluid from rest? T
Yes.
equals 0?
Yeah.
The fluid is entirely at rest.
Yeah, we start from a perfect zero, but in the laboratory it's very difficult to calm down the water. So when it's more or less calm, they start, but of course there are always noises in the laboratory, little noises. But numerically we start with a perfect calm.
And numerically,
Numerically,
R of
just calm.
T, is that 0 for T less than 0, and then something which is oscillating?
No, we
with
just
an
start with it.
amplitude? What did you specify for R of T?
The Marine has provided us with the wave maker motion. So we know that it's plus 5 centimeters, minus 5 centimeters, plus 1 centimeter, minus 5 centimeters. And we plugged it into the program.
Question. You said that the basic function in omega in domain depends on T, or they are independent on T?
Yeah, they are dependent on time.
They are independent on
They do depend on time.
They depend on time.
Mm-hmm. Yeah,
Why?
Yeah, because when we calculate the problem,
Yeah.
our grid points follow eta, the free
Yeah.
surface elevation. So when eta is bigger, then it follows. Therefore, for every z, and we make dependence only with this one point of the free surface, then every z has some dependence, gamma, so it changes proportionally following it. And when you construct the basis functions, or when you make the inversion, you see that the Jacobian, the size of the element will be.
10 years ago, Maria Zaria Padova proposed the reference scheme for reboundary problem for Navier-Stokes equations with boundary with basic function independent on G, simply sine and cosine. It
Yeah.
also works.
Yeah, I know. Brainy van Groosen also did some kind of this, so he does spectral code and he used just, the same
It's
kind
a
of.
bit to simplify a lot.
Yeah, it does. But we tried this, sort of thing.
So I guess you have to also solve a linear system at each time,
Mhm.
right?
Yeah.
But because I guess if you solve the whole domain, you probably get like something like a banded matrix.
Yeah, it is very sparse matrix, and we use PETSI linear solver to deal with it. So we write.
Direct solver.
Yeah, linear solver. Yeah,
Would you use the Betsy package?
yeah PETSI. Yeah.
But it changes at every time step because your
Yeah, we
interface
have.
changes.
Yeah, we have to recalculate the stiffness matrices every time step, which is quite.
But you have a good guess as to what the next solution is.
Mm-hmm.
Because
Yeah,
previous
yeah.
solution.
And you also have to map to regular domain or no?
Yeah, we map every finite element into the regular domain. That's what we do. But generally, what was described, it's also would be possible to map the whole computational domain
That's right.
into the simple domain.
cube.
Yeah,
That's right.
yeah, and I think it was also a paper from Thomas Bridges and Donaldson, 2010, where they do this in the variational setup for potential. So yeah. So yeah, it's also possible, but some kind of.
Can you do that with the wave maker on one side? Map it into a cube.
I have to think. Yeah, why not? Yeah, because it just I give a boundary and then I describe it. Yeah, and it's also something which we would need to do when we will be going to more complicated test cases, because in future PhD students who come just after me will have to deal with breaking waves, and in this type of connection it's not possible to do breaking waves at all, and then of course you will have to introduce some kind of mapping. Then most likely it will be the approach.
Very good. Let's thank our speaker and all the speakers.